So why do we want to reproduce the mathematics behind Rutherford scattering? Well, because it's scattering theory. It's something that we do today, that scientists do, scattering, bouncing particles off of other particles to see what comes out is what we do all the time in order to discover new particles. That's what's done. So you should understand the concept behind scattering theory. Not only that, but you should understand it just from a curiosity or learning point of view. Scattering simply means we're bouncing things off of other things. So we have, for example, what's called a scatterer, right, which would be the nucleus in Rutherford's case. So that's the scatterer. And we have the things that we're scattering, which would be the alpha particles in Rutherford's case, but it doesn't matter what they are. So let's say we send in a particle. And let's say we don't send it in, so it's on a direct collision, right? So we're sending it in on a line that's like that, so it's not a direct collision. And the distance, the perpendicular distance, it's an important concept that's called the impact parameter. Impact parameter would be the distance of closest approach, or the possible distance of closest approach. Now, what's going to happen if these are electrical is that first of all, we're going to assume, scattering theory assumes that the scatterer is stationary. It doesn't move. It's massive enough or it's stuck so it doesn't move. If it does move, then scattering theory, at least this scattering theory, doesn't work. So scatterer doesn't move. So what happens when we send this in? It is electrically repulsed, so it goes off path, right? And then it goes off, and then when it's no longer close enough to be repulsed, it's going to go off at a straight line. So it comes in with initial momentum, P initial, and a final momentum, P final. Of course, these are vectors. And obviously, B can be anything. We can't fix that. We're just going to send in a lot of scatterers at different, at any arbitrary distance to this. We're going to send in a lot of particles that are going to scatter off the scatterers, and we can't know what B is going to be. So B is going to range from maximum distance between two atoms, I guess, in this case, to minimum 0. I already said this, but I'm going to say it again. Right? There's a region. So when the particle that we're scattering comes in, I'm just going to draw it in a different color. When this particle comes in, at some point, right, it's not going to be impacted until it gets close enough, and then, it feels the electric force. Now, sure, the electric force goes infinitely far, but it goes as 1 over r squared. So at some point, it starts to feel the electric force. It will curve away, and then it's going to stop feeling the electric force, and it's going to go off, in a straight line again. So it's only going to be impacted between, two points. And so we talk about the line that it comes in on, and the line that it goes out on. Those two lines are the angle that we're interested in. This is what's called the scattering angle. Right? The angle between the incoming momentum and the outgoing momentum is the scattering angle. This is what Rutherford was measuring in his experiment. He was measuring the scattering angle. He'd send in the alpha particles, and he would see on that screen that goes around 360 degrees, his experiment, he'd see where it lit up, and that would tell you the angle at which these alpha particles were being scattered. And the goal here is to figure out how the impact parameter varies with angle. So we want to find a formula for B of theta, B as a function of theta. So for example, if I were to then measure theta, I could figure out what the impact parameter must be for that particular scattered particle. And a couple of things that might be a little bit more obvious at first. We've got to write down a lot of things in the end. For example, the magnitude of the incoming momentum equals the magnitude of the outgoing momentum. Therefore, mv initial equals mv final of the scattered particle. Not the scatterer, but the thing that's scattering it. Now, why? We said the momentum changes. It changes. Because none of that momentum is transferred to the scatterer because it doesn't move, right? Since the scatterer doesn't move, no momentum is transferred. So it's sort of like it's an elastic collision, right? It's elastic, right? In an elastic collision, if you bounce a ball off a floor, the ball, if it's perfectly elastic, will come back up to the same height of where it started, but it's changed directions, right? So it's an elastic collision. So ideally, scattering is elastic collisions. Careful, of course, again, this is for the thing that's being scattered, not the scatterer. So this is the mass of the incoming particle. Now it turns out I drew this picture a little bit asymmetrically, right? This should be pretty, yeah, the scatterer really should be over here, because it should sort of, if we look at the angle that bisects the incoming momentum and outgoing momentum, that should be equal on it should sort of be an equal symmetric on either side, because of the scatterer. So the scatterer really should be over here. Oops. Should have drawn that to begin with. Notice also that we can talk about, we can write down the change in momentum of the particle being scattered, and the change in momentum. We can just write our momentum vectors tail to tail. Pi is in that direction, Pf is in that direction. There's a theta between them. So delta P is Pf minus Pi. So Pf minus Pi is taking Pi and turning it around, Pf. And so delta P is this vector here, this vector here. That's delta P. And you can see, because if we put a bisector here, and I know I drew this a little bit messy, but if we have a right angle there, that therefore that is just an equilateral triangle, and we can figure out with just a little bit of geometry that delta P is equal to 2 times P times the sine of theta over 2, right? That's just saying, oh, look, this is, whoops, let me find a different color. That's just saying, oh, look, this is a right triangle, and the hypotenuse is MV. And so what is the size of the bottom of the right triangle? It's MV sine theta over 2, and so there's 2 of those. So it's 2MV sine theta over 2. So delta P is that, and it's in a direction along our orange axis, right? The change in momentum is in this direction, delta P. Not sure how to denote that, so I just call it the delta P hat direction. It's along that direction. Okay, so I think this is everything that's pretty obvious from just reading this picture. So let's now see if we can figure out what B of theta is from some of this. The first thing we can do with this is we can talk about what is the force that's giving us the delta P, right? It's the electric force. And delta P, we don't forget, right? Delta P is equal to m delta V. Whatever. We can talk about mv, but it's also an impulse. Remember impulse? It's equal to F dt. But what F? It's not the it's a component of the electric force. It's the component of the electric force in the delta P direction. Remember, we just made that delta P direction. This is, again, right, delta P in one dimension is F dt, is impulse. That is from the momentum chapter. In one dimension, we can write a two-dimensional equation, but in one dimension, we can just say that delta P is along the delta P direction, so we need the component of the force in the delta P direction. Force, remember, is the electric force. That's the one that we need to take the component of, right? So again, let me write in a different color. This is the component of the force between the scatterer and scatteree, component of the electric force between the things that's being scattered and the scatterer. Okay, so the electric force itself, we know, is the electric force is K Q1 Q2 over r squared in the r hat direction. This r hat direction is not the delta P direction. So we'll see that in a second, but let me just go ahead and finish plugging in here. And we get K, I'm going to write it as 1 over 4 pi epsilon 0 so we don't get our K's confused. Z1 E times Z2 E, and again Z1 is might be the thing coming in, and the Z2 is the thing that we're scattering from, the scatterer and scatteree, over r squared in the r hat direction. Now let's think about this r squared and r hat direction. I just made sure we understand that the two things that we're talking about are the thing that's being scattered and the thing it's scattering from. Here's the thing. So at some point, and I'm just calling it scatteree, that's not a normal thing, But scatterer is the normal thing, but the thing that's being scattered off the scatterer, I'm calling scatteree. At some point, it starts to feel that electric force. And let's just say, right, that's when it starts to deviate from the straight line. And so let's just say it's at this point. So at this point, it's a distance r away, right? It's a distance r away, and the r hat direction is indeed in that direction, which is why it's being pushed off that line. That's the r hat direction. Hold on. Value of r, and that value of r hat changes as the scatter E moves. And this is where it gets a little bit messy math-wise, right? So at some point it's here, and the distance r is this one here, and the r hat direction, oops, give me the right color, the r hat direction is that direction. So you can see that it changes as it goes through, right? The distance r and the r hat direction, it changes as it goes through the scattering process. So how do we deal with that? We have to do an integral. Sorry, got to do it. So arguing it away. Okay, so what we're going to do is we're going to call the angle between, again, remember the axis we're interested in is actually the component relative to the axis, that central axis. So let's just pretend that's the central axis, which we call the delta P axis. So I'm just going to, and the angle is going to go from phi to, from minus phi to positive phi or something like that. This is a different angle, right? This is the angle that the radial vector makes with the delta P axis. So therefore, F sub delta P, the force, right, because the electric force is in the radial direction, the component along the delta P axis is F delta P is equal to F, the electric force, times the cosine of phi. So we're just looking for that component, and we've got to take the integral to set that equal to delta P. So we're going to go ahead and take this equation and plug that in. Next time.